We have a special notation for this thing that we call an antiderivative. Remember that we said that big F of x is the antiderivative of little f of x if the derivative of big F of x is equal to little f of x. In other words, if you differentiate big F and that gives you little f, then big F is little f's antiderivative. Here's what that looks like in writing. The function f of x is the derivative of big F of x plus potentially some constant. If I want to find a way to write big F of x as some kind of operation on little f of x, then what I want to do is somehow undo this differentiation. In order to do that, we're going to start doing something we call integration. Integration is essentially just an undoing of differentiation. So if I want to undo d dx, I'm going to use this symbol here. It looks like an elongated S, and that is in fact what it is. Why that's the case, we'll talk about later. Remembering from algebra that what I do to one side of an equation I have to do to both sides, I need to write that integral symbol on both sides of my equation. There's another piece here, and the reason for it will become clear later on, but for now I'll just include it. And that is that when we take an integral, we sandwich it between this elongated S and dx. Again, if I do something to one side of an equation, I need to do it to both. Now, since integration is an undoing of differentiation, essentially the integral symbol and the derivative cancel each other out. That dx on the end was part of the integration, so it goes as well. And what I'm left with is that the integral of little f of x is equal to f of x plus c, big F of x plus c, its antiderivative. So instead of talking about antiderivatives all the time, I can talk about integrals. They are essentially the same thing. Okay, so let's try another example. Evaluate the integral of x to the fifth dx. What we want to ask ourselves here, since integrals and antiderivatives are essentially the same thing, is whose derivative is x to the fifth? Again, we know that when you take the derivative of a function and you end up with an x to the fifth, you must have started with an x to the sixth. The problem is that the derivative of x to the sixth is 6x to the fifth, not just x to the fifth. To account for that extra factor of 6, we divide by 6, or multiply by 1/6. And then, of course, we must include plus c, because 1/6 x to the sixth is only one possible antiderivative of x to the fifth. Let's make sure this really is right by taking the derivative of 1/6 x to the sixth. The derivative of 1/6 x to the sixth is 1/6, the constant, times the derivative of x to the sixth, which is 6x to the fifth. The 6's cancel, and we have x to the fifth. The plus c, of course, when you take its derivative, becomes 0. I wonder what would happen if instead of x to the fifth, we were integrating x to the ninth. Well, the antiderivative of x to the ninth is going to be something with an x to the 10th in it, because the derivative of x to the 10th will be a function in x to the ninth. But again, the derivative of x to the 10th is 10x to the ninth, not just x to the ninth. So we need to account for that extra factor of 10. When I take the derivative of 1/10 x to the 10th plus c, I get 1/10 times the derivative of x to the 10th, which is 10 x to the ninth, plus 0, which is x to the 9th. This is actually a very powerful rule. It turns out that it doesn't matter what power I'm taking the integral of. Let's call that power n. Then my antiderivative is always going to be 1 more, and I have to counteract by dividing by that same number. When I differentiate 1 over n plus 1 times x to the power n plus 1 plus c, I get the constant 1 over n plus 1 times the power times x to the power minus 1 plus 0. n plus 1 over n plus 1 cancels, and I'm left with just x to the n. So we have our first rule of integration, and that is that the integral of x to some power dx is equal to 1 over that power plus 1 times x to the power plus 1. Sometimes you'll see this written as x to the n plus 1 over n plus 1. Let me set one up now for you to try. Evaluate the integral of x to the 17th dx. Did you get it? Remember that our power rule says that when you're integrating x to a power, you simply write the x to 1 power higher and divide by that power. Divide by the same number. Of course, we do need to add a plus c, but that's all there is to it. Of course, there are a lot more kinds of functions than just polynomials. Let's take a look at a few of them. Note that in order to determine what the antiderivative of some of these functions are, you really just need to recognize that each function is the derivative of some other function. Let's do these a little out of order. We already know the rule for the integral of x to the n. It's x to the n plus 1 over n plus 1. In other words, you add 1 to the power and then divide by that same number. In the case where we have x to the power of 1, although we don't often write the 1, we have the same thing. I'm going to have x to the power of 1 plus 1, and then I'm going to divide by that same number. Sometimes you'll see this written as 1/2 x squared, and at other times as x squared over 2. In the same way as sometimes you'll see the general power rule as 1 over n plus 1 times x to the n plus 1. Again, don't forget, each one of these must say plus c. It could be argued that k is equal to k times x to the power of 0. If I integrate or antidifferentiate x to the 0, I'll end up with x to the 0 plus 1 divided by my new power. Of course, I need that constant term in front as well, and I also need to write plus c. If I tidy this up a little bit, I get just kx plus c. And that should make sense because the derivative of kx plus c is just k. Now, before we learned the general power rule, which is the third line here, we had to figure out how to take that integral, or how to find that antiderivative, by asking ourselves who has a derivative of x to the n, or who has a derivative of x. In the next problem, we're going to need to ask ourselves what function has a derivative of 1 over x. And you may recall from a previous section in this video that that's the natural log of x, and of course, plus c. So now we have a rule for the antiderivative of 1 over something. The last one on this screen will be the integral of e to the x. Well, if we think about whose derivative is e to the x, in other words, when you take the derivative of a function and you end up with e to the x, what was that original function? Well, that's a pretty easy one too. It's just e to the x. And then, of course, the ubiquitous plus c. It's worth taking a moment and writing these down somewhere where you can refer to them easily. There's a table in your textbook that outlines all of these and some others as well, and we'll go over a couple more in a minute. But when you actually need these, it's better not to have to stop and go look them up or rederive them. If you know them, or if you have them written down somewhere handy, that makes life a lot easier. We're going to be doing some work with some much more complex integration in this course, but these are some fundamentals that you really need to make sure you have under your belt before you get on with the harder stuff. Here's another list of integrals that we can evaluate simply by asking ourselves, whose derivative is the cosine of x? When you take the derivative of a function, and the answer is the cosine of x, then the function you must have been differentiating is the sine of x. The derivative of the sine of x is cosine of x. Because we're integrating instead of differentiating, we have to add plus c. When you differentiate cosine, you get negative sine. So the integral of negative sine is cosine plus c. When you differentiate tangent, you get secant squared. So the integral of secant squared is tangent plus c. What do you have to integrate to get negative cosecant? Cotangent, when you differentiate it, is negative cosecant squared. When you differentiate secant, you get secant times tangent. And when you differentiate cosecant, you get negative cosecant times cotangent. So here's a list of the integrals of some of the basic trigonometric functions. It's the antiderivatives that we're familiar with here. We're used to taking the derivative of sine and getting cosine. We know that when we take the derivative of secant, we get secant tangent. But since what we're doing here is an inverse operation, we need to recognize cosecant as the derivative of sine and secant tangent as the derivative of secant. If you haven't already started a list or found the one in your textbook that you can refer to easily, now would be a good time to write these down. Add them to the ones that we did a few minutes ago. I'm going to add just a few more to this list. These last few, for now, are integrals of inverse trigonometric functions. The first one, the integral of 1 over the square root of 1 plus x squared, is the sine inverse of x plus c. In other words, the derivative of the inverse sine function is 1 over root of 1 plus x squared. The antiderivative, or the integral of 1 over 1 plus x squared, is tangent inverse. And the integral of 1 over absolute x root of x squared minus 1 is secant inverse. Unless you use these formulas a lot, the derivative of sine inverse is 1 over root of 1 plus x squared. It's hard to believe you might have them memorized. In my opinion, it's not terribly important that you do. What's important is that you recognize the form that the integrand is in. The integrand is the thing inside the integral, the thing you're taking the integral of. we call that the integrand. If you recognize the form that that's in, you'll see in all of the cases in this particular screen, they're all 1 over and an x squared. Some of them have roots in them, some of them don't. But whenever I see something 1 over with an x squared, I almost always think, gosh, that looks like it might be an inverse trig function, or the antiderivative might be an inverse trig function. So keep in mind that really what's important here is that you recognize the form that the integrand is in order to save you time when you actually go to look up what the formula is. Now, your textbook doesn't list these others, and the main reason for that is that they're not used as often as the ones that I have arrows next to. They're actually also pretty easy to remember. If you know the antiderivative of 1 over 1 plus x squared is tangent inverse, then the opposite of that is cotangent inverse. The antiderivative of 1 over the root of 1 plus x squared is sine inverse. So the antiderivative of negative 1 over the root of 1 minus x squared is cosine inverse. Again, really what's important is that you recognize the form so that they're easy to find. In addition, sometimes taking an integral requires the use of a particular strategy. And the strategy that you use may depend on what your antiderivative ends up being. So again, recognizing the form is critical. Let's take a look at some of the properties of integrals. One of them is that if what you want to do is take the integral of some constant multiplied by a function, you can do so by first removing the constant to the outside of the integral and then taking the integral of just the function. Here's an example and a demonstration of why this works. Let's take the integral of 3x to the 7th dx. The antiderivative of x to the 7th is x to the 8th divided by 8. For now, I'll put 3 in front. And to check this, I'll take the derivative of the function that I have found and show that it equals 3x to the 7th. The derivative of 3 over 8 x to the 8th plus c is 3/8, the constant, times 8 times x to the 7th plus 0. The 8's cancel, and I'm left with 3x to the 7th, which is in fact the function in the integrand. So, since the derivative of 3/8 x to the 8th is 3x to the 7th, the antiderivative of 3x to the 7th is 3/8 x to the 8th. Now I'm going to do this problem again, but I'm going to do it this time by pulling a 3 out in front and rewriting the integral like this. This is just a product of 3 and the integral of x to the 7th. Well, we know that x to the 7th has an integral of x to the 7 plus 1 divided by 7 plus 1 plus c. Simplifying, I get 3/8 x to the 8th plus c. With this, we have our first property of integrals. If you're integrating a function that's preceded by a constant, you can pull the constant out in front of the integral and integrates the simpler function. Another property of integrals tells us that if what we want to do is integrate the sum of two functions, or the difference, I can achieve this by simply integrating the two functions separately and then adding or subtracting the results. Let's do an example. Evaluate the integral of x cubed plus x dx. Oftentimes you'll see the integrand, the thing you're integrating, in parentheses like this. And that just helps make it clear what it is we're integrating. What our new property tells us is that I can do this integration by first splitting the function up into its terms and integrating each of those terms separately. Now, by the power rule, I know that the integral of x cubed is x to the fourth over 4, or if you prefer, 1/4 x to the fourth. And the integral of x is, since x is x to the 1, x to the 2 over 2, or 1/2 x squared. In both cases, I have a plus c1 and a plus c2, and when I add those together, I still get a constant. So at the very end, in both cases, I'm going to have plus c. Not to mention that originally, this was one problem, one integration. So it does make sense to have just 1 plus c at the end. I've actually written this answer twice, but it's the same thing, just in two different forms. Really, whichever of those is your choice is fine. So this is another property of integrals that we'll use fairly frequently. I'd like to do one more example that combines these two. Evaluate the integral 5x cubed minus 7x squared plus 3x plus 4. We can start by separating this into separate integration problems. Take each term and put it into its own integral. Then, within each integral term, if there's a constant in the front of the term, bring that out to the front of the integral. In this last term, I do in fact have a coefficient of 4, so I can bring that out front, but then I need something to put in my integrand. I can think of that as 1, or I can think of it as x to the 0 power, and it doesn't really matter since those two are equivalent. I'll leave it as x to the 0 for now, and that will let us just use the power rule on that term like all the others. Okay, now we're ready to do the integration. In this first term, I have 5 times the integral of x cubed. That's 5 times whatever that integral is. And the integral of x cubed is x to the fourth over 4. Or again, 1/4 x to the fourth if you prefer. In the second term, I have -7 times an integral. So I'll just copy down the 7 and integrate x squared dx. The integral of x squared is x cubed over 3, or 1/3 x cubed. In my third term, I have 3 times an integral. The integral of x is x squared over 2. I can simply use the power rule here. In my last term, I have 4 times an integral, and the integral is x to the 0. The integral of x to the 0 is x to the 1 divided by 1, or x. If I tidy this up, I get for my answer 5/4 x to the 4th minus 7/3 x cubed plus 3/2 x squared plus 4x plus c. It's worth noting that the integral of a function is another function. That shouldn't come as too much of a surprise because the derivative of a function is also a function. Okay, I'm going to erase my work here, and then I'm going to write the power rule back on this screen, and we'll do one more example. This problem looks pretty nasty. Evaluate the integral of x squared plus 4 cube root x all over x dx. It's not as bad as it looks, though. In the same way that we learned how to differentiate many times by changing the form that the expression was in, that we wanted the derivative of, we can change the form that our integrand is in. If I change this integrand to x squared over x plus 4 times x to the 1/3 over x dx, and then simplify, I get the integral of x plus 4x to the negative 2/3 as my integrand. And that's a lot easier to integrate. First of all, I can separate it into the sum of two integrals, and I can pull the 4 out in front of the integral of the second term. Now I'm ready to integrate. The integral of x is x squared over 2. Then I have 4 times an integral, so I'll write 4 times whatever my answer is to that integral. My power here is negative 2/3. So if I add 1 to negative 2/3, I get positive 1/3, and then I need to divide by positive 1/3. When I'm done, of course, I'll have to add plus c. I can tidy this up just a little bit more. I'm going to say that that's x squared over 2 plus, when I invert this to multiply, I get 3. 3 times 4 is 12, so 12x to the 1/3 plus c. One more step. Since my original problem was written in radical form, not in rational exponent form, I'm going to convert that back to radical form. So my final answer is x squared over 2 plus 12 times the cube root of x plus c. That last step is just good form. It's polite mathematics, if you will. Whatever form your original problem is given in, your answer should be in the same form. That's it for this video. I'd like to make the observation that at one point when you weren't looking, I went back and added plus c to all of my formulas. That's worth making note of in your notes as well. See you in the next video.